Imagine being able to see the hidden activity inside the human body, not just its structure. SPECT makes this possible. This journey will reveal how SPECT uses gamma photons to create functional images, offering insights beyond traditional scans. After our opening, we'll explore the principles behind SPECT, examine its equipment and acquisition process, dive into image reconstruction, and finally uncover the artifacts and correction methods that shape its results. To understand SPECT, we must first grasp its basic principles. How does it use gamma photons to reconstruct images, and what sets it apart from other imaging methods? This topic lays the foundation for everything that follows. Let's start by defining SPECT. Single photon emission computed tomography is a nuclear medicine imaging technique that reconstructs cross-sectional images from multiple gamma photon projections. This definition highlights the unique approach SPECT takes, using emitted photons to visualize internal activity. Here's how SPECT works, from detecting gamma photons to reconstructing activity maps that reveal functional information. Gamma photon detection is central to SPECT, as it captures photons emitted from active regions, forming a signal profile at each acquisition angle. Projection acquisition involves integrating the source activity along each ray path, allowing SPECT to collect information from multiple directions. Image reconstruction is the process of building tomographic cross-sectional images from these projections, revealing the internal distribution of activity. Activity mapping in SPECT reconstructs the activity, measured in per second, rather than attenuation mu, which is typical in CORT. Comparing SPECT and X-ray CT helps us understand their similarities and differences, especially in how they reconstruct images and what they measure. For detector type, SPECT uses a planar gamma camera, while X-ray CT relies on an X-ray detector. This difference shapes how each system captures data. In image reconstruction, SPECT prefers iterative methods due to photon noise and fewer views, whereas X-ray CT commonly uses filtered back projection. The measured quantity in SPECT is activity, which is measured in per second, while X-ray CT measures attenuation, represented by mu. Acquisition speed is slower in SPECT because it cannot count photons as quickly, while X-ray CT is much faster. Now that we know the principles, let's look at the equipment and acquisition process. How do gamma cameras and their configurations impact the efficiency and quality of SPECT imaging? Gamma camera configurations play a crucial role in SPECT, affecting both efficiency and versatility. Multiple camera heads are used in SPECT to increase photon collection efficiency, capturing more data in less time. Rotating cameras allow for both scintigraphy and SPECT, providing flexibility in imaging techniques. Let's trace the chain of events in the SPECT acquisition process, from initial setup to final projection collection. Camera setup involves positioning the gamma camera heads around the patient, preparing for data collection. Rotation around the patient is performed sequentially, allowing the cameras to capture projections from multiple angles. Projection acquisition is the stage where data is collected at each position, forming the basis for image reconstruction. Multiple projections are acquired over 30 to 60 minutes, typically resulting in 64 to 128 views for comprehensive imaging. With the data collected, the next challenge is reconstructing images. What methods are used, and why are some techniques preferred over others in SPECT? Reconstruction methods in SPECT range from filtered back projection to iterative techniques, each with its own strengths and limitations. Filtered back projection is standard in CT, but less ideal for SPECT due to low photon flux and fewer views. Iterative reconstruction, such as algebraic reconstruction technique, is preferred for SPECT and can include collimator detector response for improved accuracy. Iterative algorithms offer deeper insights by simulating real-world conditions and refining results through comparison. Iterative algorithms incorporate non-idealities by simulating projections with all known factors, making each guess more accurate. Comparison with observed data allows the algorithm to refine the distribution of radioactivity, improving image quality with each iteration. Even with advanced techniques, SPECT images can suffer from artifacts. What causes these distortions, and how can they be corrected to ensure accurate results? Scatter artifacts are a major challenge in SPECT, but energy window adjustments can help mitigate their impact. Detected scattered photons in SPECT lead to reduced spatial resolution and contrast, making images less clear. Adjusting the energy window can reduce the effect of scatter, helping to improve image quality. Attenuation artifacts arise from tissue interactions, but correction algorithms can help reduce their effects, especially for larger objects. Tissue interactions affect projections and cause artifacts, especially when attenuation is ignored during reconstruction. The impact of object size is significant, as artifacts increase with larger objects when attenuation correction is not applied. Attenuation correction algorithms, often iterative, use anatomical knowledge from sources like CT to minimize artifacts. SPECT imaging goes beyond structural scans, revealing the dynamic activity within the body. By providing functional insights, SPECT continues to drive medical innovation, offering new ways to diagnose and understand disease.